happy to introduce our guest, distinguished professor from Zurich, expert in quantum informatics and quantum cryptography, interested in various things in which we cross a little bit in interpretation of quantum mechanics and some other issue. And today, Renata will deliver the lecture on quantum cryptography, what kind of problems there are, what are perspectives in this topics, maybe most developed in real technology, right?
Mm-hmm. Yes.
Yeah. So, please.
Okay. Welcome, and first would like to thank Gordey for inviting me. It's a pleasure to be here and to see, to have met so many bright people. I'm really impressed by the place, I have to say. So I will certainly return if I can. I will talk today about quantum cryptography, and I was told that at least the beginning of the lecture should be kind of on an introductory level. So even if you haven't heard much about quantum cryptography, you should be able to follow the first part of it. Maybe towards the end I will say some more technical things. But as was just mentioned, it's important maybe to know as a motivation that quantum cryptography was one of the first inventions of quantum information. So in '84, when the first protocol was proposed by Gilles Brassard and Charlie Bennett, this was almost unnoticed by the physics community. And then '91, Arthur Eckert wrote another paper where he somehow reinvented quantum cryptography. He didn't know about the other thing, as he said. And then this was a paper in Physical Review Letters. Then people started to realize that this could be interesting. And the whole development of quantum information and computation was not only triggered by the idea of building a quantum computer, but also by the idea of doing very safe and very secure cryptography. And today, I would say quantum cryptography is really the most far developed application of quantum technologies. So there exist now commercial schemes. There's a company, for example, even in Switzerland, where I'm from, there is a company in Geneva which sells quantum cryptographic devices. They're still quite expensive, so it's of the order of 100,000 euros that you have to pay just to communicate from A to B. But for certain high security applications, as they are required by banks, for example, this is of interest. So this is what I'm now talking about is something that actually exists in practice. I'm just saying that because sometimes when I start talking, people think, okay, this sounds very hypothetical, but it actually exists. So you're talking about the real thing. So let me now start with the basic idea behind quantum cryptography. And I will somehow try to really give you the full story of how it works, but I will drop certain technical details which are not required for a, let's say, understanding of the basic concepts. So I will, as a first simplification for the moment, assume that we have no noise in the processing of things. So we can essentially create quantum systems in a certain state, and we can measure them perfectly, and so on. Of course, in practice, this is not the case, and one has to deal with the imperfections, and it's not easy to deal with them, but we can do that. But for the moment, I would like you to think of an ideal situation where we can essentially really do the things we want to do with quantum systems. So what is now the idea? So in quantum cryptography, we have usually two parties, and they're called Alice and Bob. And now I tell you immediately how they can actually generate the key. And that will be the purpose of quantum cryptography. Maybe for those who are not familiar with this at all, one thing you should note is that in quantum cryptography, we are not talking directly about the scheme which allows Alice to send a secret message to Bob. But that's, of course, what we want to do. So we want Alice to be able to send a secret to Bob in such a way, so there's a channel, and we can think of some adversary, that's Eve. The adversary tries to listen to this channel, and although the adversary has full control over the channel, he could essentially cut the channel or do anything to it. We still want that when Alice sends it to Bob, only Bob can read the message and no one else. So in particular, Eve, the adversary, cannot read it. But now this is kind of complicated to talk about messages and so on. So what we are now going to do is to look at something simpler. We will just ask the question, is it possible for Alice to do something which allows her to generate something that I call a key? And it's usually called S for secret key, and Bob as well. So what is S? S is just, you can think of S as a string of bits, 0 and 1s of a certain length. And you want Alice and Bob to generate the same key. And the requirement, so this, maybe I call this SA for Alice and SB for Bob. And the requirement is that they have the same thing. And the other requirement is that Eve knows nothing about SA. So what does it mean that she knows nothing about the string? It essentially means that the string S, I mean, I can now just call it S because they're equal. S is uniformly distributed from her point of view. So even if she uses everything she can possibly have, all information, conditioned on that information, so it's uniformly distributed on the set of all possible strings. So each, from her viewpoint, each string is equally likely. And now once, and this is the connection to sending messages, once you have such a string of L bits, there is a classical cryptographic scheme, which is called the one-time pad encryption scheme. The idea is essentially to, if you want to send a message, a bit, you just add a key bit to the message bit and add modulo 2, so this gives you a new bit, and you send that bit to Bob. So Alice encrypts by just adding a key bit to a message bit. And Bob subtracts the key bit again from the message bit to decrypt the message. And so then one can show that if the key is completely unknown to the adversary, if the adversary now sees this encrypted message, it doesn't give her any information about the real content. But of course, if you know the key, you can decrypt it. So because of this one-time pad scheme, we can now just focus on the simpler task of generating a key. So what you should get from here is just, once we know how Alice and Bob can generate the key, and by key I mean this, a uniformly distributed bit string, which is the same for them, then they can use this bit string to communicate securely. But there's one important thing. If you use this bit string to communicate, you have to use a new bit, a fresh bit for each message bit you want to send. That's, by the way, why the key is called one-time pad. So actually, maybe I should very briefly write that down. So if you have a message bit, so M should be a message bit, and a key bit, S, then you generate the ciphertext using doing this. So C is the, and you actually send C, and so what Bob does, he takes C and generates M by computing C again X. So this little plus means an addition modulo 2, and so you can easily verify that it gives you the message back, but you can also verify that the C alone, if S is random, is just a random value. Now, in order for this to be random, you need to generate a new key bit for each message bit. And there's actually a story that is told in the Western world, and I'm not sure it's true, and maybe you know that much better, because it's a story about the Cold War and about Russia. So there's the story, and this is something that is on the web available, but I'm still not sure it's actually true. The story says that the communication between the embassy that Russia had in the US and Moscow was secured via such a one-time pad channel. Of course, this key S was not generated with quantum technology, because that was a long time ago, but what they did, instead of generating this S with quantum technology, they just generated a long tape, magnetic tape with random bits, and copied it and sent one copy physically, like the tape. They flew it over to the US, and then they encrypted with one of the tapes here. They used it to encrypt and decrypted with the other one. And then what happened is that at some point they run out of keys, so they have used the whole tape. So they started to reuse the whole thing again. And that's something you shouldn't do because it's a one-time pad. So it turned out that the NSA, the US Secrecy Service, could decrypt all the communication because this key was used twice. And this communication is now, after the archives are open, now publicly available on some server of the NSA. So you can actually check that. So as I said, I'm not sure whether this is all made up, but there is an internet site of which it's called the Vernon Project. And if you Google that, you can find all these documents that were exchanged between the Russian embassy and Moscow, which were hacked by the US Secrecy Service. So the point of this story is that you shouldn't really reuse the key. So what quantum cryptography does is to generate such keys. And now we go to a more technical level. The question is how can we use quantum mechanics to achieve this goal, to generate random bit strings which are unknown to an adversary. So that's what we are now going to do. But by the way, if anything is unclear, I'm of course happy to take questions anytime. So I will now tell you how this works, and I will focus on what we call an entanglement-based scheme. And suppose for the moment, I will again now make an assumption which we will later justify. Suppose that Alice and Bob are able to somehow generate a pair of entangled qubits. So what do I mean by that? So this is a qubit A, and this is a qubit B, and the whole qubit is in a state which I call phi AB, which is just a superposition of zeros and ones. So it's in this state here. So it's 0 on A and 0 on B. And with an equal probability or equal amplitude, it's just a 1 on A and a 1 on B. Now the idea is that suppose that we really know that they have this state. And I will later tell you how they can know. But let's suppose they know that. The idea is that Alice can just measure her system in a computational basis. So she can measure with respect to the 0-1 basis. And Bob does the same thing. So Bob also applies a measurement with respect to the 0-1 basis. Now, what does come out if you measure like that? Of course, you can easily see if you measure in the 0-1 basis, with probability 1/2, both of them will get a 0, and with probability 1/2, both of them get a 1. So certainly they are equal, the bits that they get. So now I'm talking about the single bit. So L here is in this case just 1, but of course we can repeat it. But the question is it true that Eve knows nothing? And this is the harder question, and this is kind of now coming to a core point of quantum cryptography, because whenever we do such a thing classically, we would never be able to guarantee that Eve knows nothing. So how can we now argue that if we do this, the adversary cannot know anything about the value, about the measurement outcome? And to do that, it's actually very simple in this case to argue why the adversary knows nothing. Of course, you can say the adversary doesn't have anything, but maybe the adversary has some correlated piece of information which may be somehow correlated to what Alice and Bob measure. So how can we prove that this is not the case? And for that, I will write down a little lemma which is almost trivial to prove. You can, if you have heard some quantum mechanics, you should actually be able to do it just in 5 minutes or so. So what does the lemma say? The lemma says the following. If any quantum state, so by quantum state I mean a density operator, technically, rho, and let's suppose I have a quantum state on 3 systems. So I assume that there is somewhere an adversary, Eve, in this picture, and Eve has some information. And I don't make any, so this is now important, I make no assumption about what information the adversary has at the point where this entanglement was distributed. I just assume she has some information, and all the information that the adversary has is stored in a quantum system E. So this is now not necessarily a qubit. This can be an arbitrarily large quantum system. And now I'm making a statement about a state which has, is defined on 3 systems, A, B, and E. And now I make one assumption about this state. The assumption about this state is the following, namely that if I trace out the system E, so if I just essentially ignore the system E and look at the marginal on AB, then this state is equal to the state that we have. So you see, according to to what I said, we are assuming that Alice and Bob have this particular quantum state, phi AB, this so-called Bell state. So the only assumption I'm making is that the tripartite state that describes everything, Alice, Bob, and Eve, is compatible with the fact that if I only look at Alice and Bob, they have an entangled state. And now the lemma says that whenever this is fulfilled, then this state rho ABE is actually a product state. So it's of the form rho AB, or maybe I can just here be even explicit, phi AB tensor rho E. And this is just some I mean, you can say this is just a trace of rho ABE traced over A and B. So as I said, this is almost trivial. If you have some knowledge in quantum mechanics, this is almost obvious. But I will later give you a proof of a more general version of this. So don't worry if you don't see it. But it's actually a nice exercise. But why is it? Yes?
Can you please explain the process of information in one case with some more details?
Sorry, with some?
I just don't understand what's happening in quantum case. You have 2 bits and...
Yes, so, okay, maybe I should say, so the assumption, this is at the moment an assumption which I will later justify. So the assumption is that Alice has a qubit and Bob has a qubit. And for some reason, which I will later justify, the 2 qubits are in this state.
Okay.
So now, later we will see how Alice and Bob can really make sure they have a qubit in this, 2 qubits in this state, because it's generally hard to achieve that. But let's for the moment assume that for some reason they know that their qubits are in this entangled state. And now the only thing they are doing is Alice measures her qubit in the basis 0, 1, and Bob... The one in A, yes. And Bob measures the B system. And they get an outcome. And I say the outcome of this measurement is now the key SA. And the outcome of this measurement is the key SB. And now what I said is...
They do several measurements.
Yes, but let's for the moment assume we just generate 1 key bit. At the end, they would repeat that. They would take a new state. Of course, to do a new measurement, they would have to take new qubits, because
they are generating encoding pattern S, yeah, making several measurements.
yeah. So they repeat the. So let's say you could think of they generate this state on 2 qubits, and then Alice measures once and Bob measures once, but then they repeat the whole thing. They generate a new state, and then again Alice measures this and Bob measures this, and each time they repeat the process, they get 1 bit of a key. And so if they repeat it L times, they will have this key of L bits that we want to have. So this is essentially the process to generate 1 key bit. But we can repeat the whole process. But to repeat it, we have to generate a new state, because, of course, the measurement will destroy, in general, the state. Now, why is this lemma important? So this lemma tells us that if Alice and Bob can really be sure that they have this state, then they can also be sure that whatever the adversary has is completely independent. So what does it mean? It just means if the piece of the state that Eve owns is statistically independent of what Alice and Bob have. And that's what we would like to have. That's very important. It means that whatever Eve could potentially possess is actually not correlated to the state itself. And now, there is another thing you have to notice. If we now have a state of this form, of this product form, and we generate a key, then this key will also be independent of E. So let's say if you want to have a picture of this, then I would say we have here A and B and E, and we know that this thing here, this is in a state rho AB, and this thing is in a state rho E. They are independent of each other. But now the key is generated by a local measurement here, and this key is generated by a local measurement of B. So if I now look at the probability distribution of the two keys, SA and SB, then it must still be independent of what the adversary has. Because clearly, if I have a system like A and B, which is completely independent of E, if I do something locally on this system, like a measurement, I'm still independent of this. I cannot generate correlations by doing something local. And this is all what you need to actually argue that this key SA and SB is now perfectly secret. Because we already know by just looking at, I mean, you can, of course, calculate this probability distribution. That's trivial. It's just 1/2, 1/2. If probability 1/2, it's a 0, and if probability 1/2, it's 1. But in addition, you now know that there's no correlation between these outcomes and the piece of information that the adversary has. And I would say this is really the core of why. So if you ask why does quantum cryptography work, it's actually this almost trivial lemma which tells us that if we have a pure state on A and B, in particular this Bell state, then necessarily everything else, whatever it is completely decorrelated from it. And that's something which is remarkable. So that's why I'm stressing this. Because in the classical world, we could never say that. If I say I have a probability distribution between A, B, and E, if A, B, and E were random variables, and I just know what is the probability distribution if I only look at A and B, then there's no way I can say that the third random variable, E, is correlated or not correlated to A and B. I don't know anything about it. But in quantum mechanics, by only knowing a property about A and B, I can infer that any other system is independent of it. And that's at the end the reason why it works. So that's why we get secrecy from quantum and not from the classical world, because such a lemma couldn't be true classically. So it's important that you see the significance of this lemma. This is really about secrecy that we have here, this tensor product. Of course, this doesn't now tell you how you do really quantum cryptography, because I was now assuming we have such a state. But what I hopefully convinced you so far is once we know how to generate an entangled state of this form between Alice and Bob, then we have a secret key. Alice and Bob just have to measure it and they have the key. So now we can focus on the next separate question, unless there are now questions by you. I would now focus on the question, how can Alice and Bob generate such a state? And the difficulty here is that, of course, in cryptography, they don't have a trusted channel. So even if, let's say, if they had perfect technology, Alice could, for example, generate 2 entangled qubits in her lab and then send 1 qubit to Bob. But of course, there's no reason to believe that this qubit that she sends to Bob arrives at Bob and not at Eve's position. So the question is, how can we actually distribute entanglement and be sure that it's not in the hands of the adversary? And that's now, but once we have that, then you essentially know how, in principle, quantum cryptography works. And this is, in some way, similarly elegant or easy to achieve. So I will now erase this lemma and instead write here some different thing. And now we have to go to something which relates to the question that you asked, which is so in general, we don't do this only once. We repeat it many times. And maybe I draw a picture for that. So you could imagine that, if you have here Alice and Bob, then they're generating a qubit, which is entangled, like that. And let's now suppose for the moment that they would really just try to do it. So they know there is an adversary, but they would still just try distributing this thing. So you could really think of an actual cryptographic scheme where Alice has some means to generate 1 photon which is entangled with another photon. She keeps 1 photon and sends the other photon to Bob. over an insecure channel. So if the adversary wasn't capable to capture it, and if the channel is perfect, which we assume for the moment, then we have entanglement between Alice and Bob. And now they could repeat that. And let's suppose they first repeat that and do all the measurements only at the end. So, of course, I mean, that would be unrealistic, but to conceptually understand what's going on, it's useful to think that we distribute many entangled pairs and measure all of them at the very end. Of course, in practice, you measure them immediately, but this doesn't matter so much for the moment. So then the situation would look schematically like this. So this wiggly line always indicates that we have a state of the form phi, which is defined like that. So this would be a ket vector phi. That's what I have to say here. So that would be the ideal situation. But now, maybe the adversary destroyed it. So this is, maybe I call this here ideal. So what is actually the real situation we have? Probably. So in reality, what could the adversary do? The adversary could, when Alice sends the qubit to Bob, the adversary could just keep it and send something else to Bob. So maybe in reality, Bob gets something which is kind of independent of Alice. But the adversary could even do worse things. The adversary could, for example, take Alice's qubit and store it, for example, and not send anything to Bob. So he does, again, get something independent. But maybe she sends this qubit that Alice sent in the second round in the third round to Bob, just to confuse him. So this would end up in a situation where Alice in the second round is somehow correlated to Bob in the third round, but they wouldn't know that. So, but the bottom line is, at the end of the day, when they do that, and if the adversary is really malicious, then the correlation could have an arbitrary pattern. So I just draw it schematically like that. So you have correlation potentially between everything and also Eve. So that's what an adversary could do. She could just mess up everything. So that's what we have really. And now the challenge in cryptography is kind of to detect such situations and make sure we have only this situation here. So that's really what one has to do in cryptography. And how is this achieved? Let me now introduce another assumption for the moment, temporarily, and later we will drop it again. So this is like this is the ideal thing, this is the real thing, and I will now have something intermediate. And in the intermediate, I will assume that the adversary is not completely malicious. The adversary will just, each time Alice sends something, will do exactly the same to the qubit. So she has some strategy of what to do, and she always does this thing that she wants to do with it. So maybe what that means is that she gets some information about it, so they're maybe all correlated. And there is some arbitrary state which I could write as A, B, E, which characterizes what Alice and Bob have. But in each round, it's the same. So there's some state row A, B. Maybe I don't write the E. This is too complicated. So there's some state between Alice and Bob. But because Eve, the adversary, is reasonably nice, it's always the same state that they have. But maybe it's a completely uncorrelated state. So we don't know that. But now comes the next idea of quantum cryptography. So let's now suppose that at least we know that each time Eve does the same. So what we can now do is to do something which is known as sampling, or also tomographic sampling. We could just say, OK, Alice and Bob select some positions of them. Let's say they take the first three or some random ones. Let's say, I don't know whether I have colors here, probably not. But OK, let's say they say, OK, let's test this one, and let's test this one here. Now, what you should know in quantum mechanics is that if I give you many copies of the same state, and you can do measurements that you like, then you can always find out what the state is. There's always it's called an informationally complete measurement. So this is a well-known fact about quantum mechanics, and in addition, you can even do it locally. So if Alice and Bob just do local measurements, so Alice measures on A and Bob measures on B, if they do sufficiently many measurements and collect statistics, then they can figure out what the state is. But this only works if you always get the same copy. If I just give you once a quantum state, and you are only allowed to measure once, or use that one, you will not be able to figure out what the quantum state was. But if I give you a promise and say, I give you 1 million of the same quantum states, and you can do whatever measurements you like, then you can find out what the quantum state was. So now in cryptography, we use exactly this idea. We say that Alice and Bob just select a few of them. I mean, you should maybe think of, like, to have some measures in mind. There are maybe 10 million such pairs that we are sending in total. And maybe you select from these 10,000 which you use for that test. So you have still many left, which you can actually then later use as for the measurement. So now if you get these 10,000 things, Alice and Bob can figure out what is the state rho AB. And they can just check, is the state rho AB this particular state they want to have, or is it at least close enough to that one? And that's what one does in quantum cryptography, essentially. So, by the way, for those who are experts, there are two different schemes. One is called entanglement-based scheme, and one is prepared and measured. And here I'm talking about the entanglement-based one. So in the entanglement-based one, you can really think of it, Alice and Bob just distribute entanglement, and now they just check on a few random positions and do measurements to find out what is the state. If they find out that this state rho AB is not this Bell state, so this means that the adversary has really corrupted something, then they just abort the protocol and restart. If it was the correct Bell state, then they can proceed with the measurement of the remaining ones, because if they tested a few of them, they know all the others here by assumption are in the same state. So now they are sure that this assumption that I made here is now fulfilled, and they can just measure them and get the key out. So by the way, this also shows you that quantum cryptography doesn't guarantee you that you can always generate the key. What quantum cryptography does is you can detect whether there is an adversary in the line. So you should see quantum cryptography more like something where, let's say I have a messenger. Like the classical analog would be, I want to send something to Gorday from Switzerland. So I send a messenger, my friend, to Gorday. And let's say he's a trusted friend. Now I cannot avoid the possibility that someone kills my friend on the way and it will never arrive. But Gorday will notice that he doesn't arrive, and I can just send another friend and try again, and maybe he arrives. So that's what quantum cryptography does. It doesn't guarantee that the friend arrives. On the other hand, if it's a trusted friend and if he arrives, then Gorday will be certain that the message was the correct message delivered, and if it's a trusted guy, he will know that it wasn't read by anyone else. So that's what quantum cryptography achieves. It achieves that if the adversary doesn't capture the message, the thing, then it arrives. But by the way, that's nice that we have this two-stage process. So here we are just generating a key. So if the adversary does something bad, there was not a message yet sent. So it's just, we couldn't generate the key, and I would try it again. And at some point, maybe the adversary gives up and says, OK, I don't do anything. And then we get an entangled state, and then we can extract the key and send the actual message. So that's the idea. Yes?
Yeah, one question about the test. Say you are taking 10,000 qubits.
Yes.
Sending Alice promised that she sent the only one state, Bob measured it, yeah? So Bob can figure out what the message was. But how will he confirm?
Yes, so this is a very good question. So in quantum cryptography, we still assume that, OK, we assume we have no secrecy at all. So it's like the internet. But we assume still that we have an authentic communication backwards. So we assume that somehow at the end, if I come back to the example of the messenger, Gorday can call me and tell me, actually, the messenger arrived. So by the way, in the example, to make it more close to that, would be that I don't give the messenger the message. I just give him a random bit, which he conveys to Gorday. And if the bit arrived, Gorday will call me and say, oh, the bit arrived. Now I can send the real message bit.
Yeah.
But
tells you that the bit is, he tells you what the bit is, and then OK,
No, okay, this is now, so I would now repeat that many times. So maybe it's actually a good example. So let's say I send 1 million bits to Gorday in that way. He will call me and tell me at certain positions, let's say he would tell me the second bit was a 1 and the 100th bit was a 0. And he does that for many positions. If all these positions agree with the bits I sent, then I'm pretty sure that nothing was changed, at least statistically. So this is like this test. Now, the other bits, he doesn't tell me, this is the ones we want to use for actually securing the message. So the others, of course, the ones he told me on the phone are now insecure because the adversary could have listened to the phone call. But he only does that for, let's say, 10,000. But I sent him 1 million. So you have still 1 million minus 10,000 bits, of which I'm now pretty sure they are unchanged. Of course, there may be some which are changed, but statistically, I can calculate that the probability for an individual one being unchanged is pretty good, is pretty low. So now I use the other ones. So yes?
If the phone is on secure channel, how do you know that it's actually Gorday calling you?
Yes, okay, and this is now the, so what we assume that the communication back is still authentic. So which means that it's by assumption we assume that I know his voice and so on. Now you can ask why is this realistic? So now this is now classical cryptography. So in classical cryptography there are perfectly secure schemes which allow us to, if I have some initial password, let's say, that only me and Gorday knows, then there's a way, which is now has nothing to do with quantum cryptography, that he can give me an answer in a way such that someone who doesn't know the password cannot change that answer. This is called authentic communication. So in some way, I don't need to really assume that. The only thing I need to assume is that we have some shared secret, and that we anyway need, because there must be something that distinguishes Gorday from an adversary. And what distinguishes him from an adversary is that he knows the password. I mean, there's no other way I can tell a person. I mean, I have to somehow identify the person with the message.
And you can give him a password securely.
Yes.
You can give him bits securely.
Yes. So maybe. Yes. So that's also a very good question. Thanks for asking it. It's an excellent question. Actually, this is often criticized about quantum cryptography, but quantum cryptography exactly solves this problem that I mentioned with the embassy of the Soviet Union, because initially, at some point, before we start the secret communication, we need to meet at some point and exchange a short key. This can be very short. It can be 100 bits or 200 bits. That's sufficient. But then, once we separate, and I'm in Zurich and he's in Moscow, we, of course, want to continue talking. And we couldn't, I mean, I don't want to exchange with him initially as many bits as we will ever exchange in our future conversations. That's exactly the problem with the magnetic tape. They run out of the magnetic tape because at some point. So what quantum cryptography does is essentially it now generates a stream of new bits once you have an initial one. That's why some people call quantum cryptography quantum key expansion, which is maybe a more fair term. So you start with something very small, but you have to start with some secret. And then you can expand it and make it arbitrarily large by communication. So the same, or the initial? Ah, no, then you regenerate new ones for the authentic communication out of the key you generate. Yes. So in this sense, the quantum cryptography doesn't solve the problem that if I want to communicate securely with a person, I once need to meet the person. But there's provably no other solution to that if you want to be information theoretically secure. So even classical cryptography needs an authentic channel at some point. So for example, if I have my bank, at some point I get a hard copy envelope sent from my bank, which I can use for my e-banking. But I cannot start the communication with my bank over electronic means without ever having been at the counter and exchanged something. This is a problem. This is a fundamental fact of cryptography that we cannot overcome that. So the authentication problem is not resolved by quantum cryptography, only the secrecy problem. Okay, so now what I have said is essentially that if we make this additional assumption that Eve always behaves in the same manner, then we can test what she does, and if she didn't do anything harmful, we get this state, and we can now be sure that we can generate the bits. But now I've still made a very important assumption. I've assumed that she always does the same, and there is, of course, no reason for the adversary to be so nice and always do the same. She could just do this big mess here, and then this method doesn't work. And by the way, this is now the really hard part of the security proofs, because this thing is quite easy to get. You just use standard techniques from tomography and so on. And that's why the first security proofs until the year, actually, I think 1999, when Shor had a nice idea to resolve the problem, were all based on the assumption that Eve is nice. So this is remarkable. So even 16 or 15 years after the invention of cryptography, one couldn't actually prove that it's secret. And the reason is really that an attack could just be arbitrarily complicated. And this is at the end an arbitrary state on an arbitrarily large Hilbert space. So it's very hard to make statements about it. But nowadays we have several methods available which allow us to essentially go from this scenario to here without really introducing an additional assumption. And this is now something I would like, which is a bit more technical, which I would like to talk about. Yes? You have
One last question. What's the difference between ideal and intermediate?
So the ideal one is just, I assume the adversary does nothing. So I really have the actual, so Alice in the actual protocol would really prepare a Bell state locally in her lab between two photons and send one photon to Bob. So in this case, if there's no adversary, we already know we don't even need to test it. We just have to see. So this intermediate is where the adversary can attack it.
But not in terms of A1, A2?
Yes, she just does, each time a photon is sent, she applies essentially the same operation to it. So she has one strategy, but each time she exactly does the same strategy. And if she always does the same strategy, we always get the same states.
And ideal is not Eve.
Yes, it's essentially Eve is passive, if you want, in some way. Now, this is, I don't know about the time, so how much time is left?
Just like usual lecture, you have 40 minutes.
Left. Okay, so then I will probably first talk about a technique which is very general, applicable, and is actually maybe of interest beyond quantum cryptography. And this is called the Definetti reduction technique. And I think even if you haven't now understood anything about quantum cryptography, this is something that may be of completely independent interest, but it exactly solves this problem of coming from here to here. And then I will give something more or a different approach, which is also leads to current research to give you some perspective of what are the open problems today. So let me therefore briefly say something which is just very general and just about a property of systems which have many parts. This is, if you look for a keyword, this is called the Definetti approach. So Definetti is an Italian mathematician who lived long before the quantum era. So he developed a theorem which is very well known in classical probability theory. You probably have heard of it. But what we are going to use is a quantum version of this theorem. So what does this theorem say? So suppose that I have many systems. So now I will just call systems SI. So these are now not keys. So now I'm not talking about cryptography. So we have just many systems, S1, S2, S3, until Sn. And let's suppose we have some big quantum state on the system. I mean, big quantum state means we look at the joint quantum state, the joint density operator of all these systems. And let's, for simplicity, assume that all these systems are modeled by the same Hilbert space. So they have all the same dimension, if you like. Now, this state can in principle be arbitrarily complicated. It could be a state like here where, let's say, this is entangled with this and everything is correlated. But let's now make one assumption about this state. And we say this, say them permutation invariant. So so this state here is called permutation invariant if a pretty obvious condition holds. If I permute any of the system indices, so if I somehow, instead of looking at this state, I look at the state where instead the first system is now some system which I call pi1, and the second system is one I call s pi 2, and so on, until s pi n. And where pi is a permutation, is any permutation on the indices. So I just somehow mix the order, I reorder the systems in an arbitrary way. I can of course do that. And now, if I reorder the system, sometimes the state describing all the systems is still the same state. So for example, this is the case if I mean, a good example of such a state, maybe I write this here, is something like what people sometimes call a GHZ state. Of course, there are even trivial examples, like a product state. Maybe I should start with that one. So an example of a permutation invariant state is that rho S1 until Sn is just some sigma, which is only on one system, S tensor n. So I just take the same system and tensor it n times. Then obviously, if I permute them, this doesn't change anything. But another example is if the state is actually a pure state. I call it psi, and where psi is a superposition. This is a less trivial example. Let's say it's a superposition of many zeros. So I have all systems are in the state 0, and with probability, this is like an extension of the Bell state. So it's a Bell state where instead of 2 systems, I have n. So again, this is not a product state, obviously. It's a highly entangled state, but still it has the property that if I exchange the systems, then it remains the same state. Now, De Finetti proved the following theorem, and maybe I will now move here to this board. He made a very strong statement about the structure of such states. Of course, he did it for classical probability distributions, but nowadays we have a version for quantum probability. So the statement is essentially like that. So there's a theorem, and I will now write an informal version of the theorem because the theorem has some parameters which I don't want to reproduce exactly, but I will give you an idea of what they are. So the theorem says the following. If rho S1 to Sn is permutation invariant, then if I look at a part of the state, so I now somehow look at only, let's say, k different systems, where k is smaller than n. So what I mean by that is that I trace out n minus k systems. I just throw some away of them. So I have a new state, which is just describing, let's say, I just look at those here until here. Let's say here is sk. Then this state here is somehow close to a state which has the following form. It's a state where I have an integral, and then sigma s tensor n. And now this approximation holds if k is sufficiently smaller than n. So, okay, let me now explain what that means. So this means the following. Sorry, I made a mistake. This is, of course, only for k systems. So what does this mean? So there's an integral here, and there's some measure sigma. We don't know anything about this measure. You can see this just as a, I could also have written a sum over many such things. So essentially, you can think of it as a convex combination of states of that form. So what this theorem tells me is that if I know that all these systems together are invariant under permutations, then if I now only look at a small part, I only look at K systems, and I look what are the structure of these systems, then I know that they are essentially of this very nice form. They are just product systems. They are uncorrelated of each other and the same. So that's what this means. So this just means essentially I have many independent things which are identical and not correlated among them. And however, I don't have just one, I have a convex combination. And by the way, for this example, you can easily see that here what you get, even if K is by 1 smaller than n, what I get is a state which is a convex combination with weight 1/2 of a state which is just a product of 0 states and a state which is a product of 1 states. But it's no longer a superposition if I trace out one. I just get a mixture. So in this case, this would just consist of 2 components. So you could really replace the integral just by a sum of 2. But the Definetti theorem tells us that this is always the case. Okay, so that's the theorem. Are there any questions about the theorem itself? Okay, so why is this theorem now useful for cryptography? And maybe I will just very briefly redraw a part which I had here, which is about the structure of the states. So before, you remember I had this very complicated structure of A1 and B1 and so on. And let me not draw everything, but there was something like A, Bn, and there was some arbitrary thing here in between. Now, to connect this to the Definetti theorem, I could say, let's just look at a pair of such things as one system. I call this S1. And then there's a next pair, and this I call A2, and here B2, and so on. And now, let's suppose that the adversary is now a bit less nice, but still nice enough to make sure that we know that the state that is generated between Alice and Bob are permutation invariant, in the sense that if I would exchange the first and the second or something else, I wouldn't change the state. So this is still an assumption, but let's suppose we make this assumption. Now, what the Definetti theorem tells us is that if we now ignore a few systems, so if I, let's say, don't consider the second one, and maybe I don't consider the last one, I just throw away a few, and I keep the remaining ones, then they are in a product state where this is in a product with this, and so on, they're all identical. But this is exactly the situation we had before. So now I just dropped a few. Maybe the A3 system is not here, and maybe there's only the n-1 and not the n, or so on. But now I'm really, the Definetti theorem tells me that it's sufficient. So as long as I'm ready to ignore a few systems, and remember that we anyway used up a few systems for this like tomography thing, and in practice you will anyway lose a few. So if you don't consider all of them, then if it's sufficient to assume that we have permutation invariance here, and then we can already be back in this, what I called before, the intermediate situation. So now maybe to be consistent with the theorem, this would be the sigma, where sigma would now be a state on A, B, and it's always the same. So the S is now always an A and a B. So in other words, in quantum cryptography, to arrive at this nice situation for which we know how to prove things, it's sufficient to actually assume that we have a permutation invariance here. And now you could ask, why is it now less bad to assume that there is a permutation invariant? Because this was still an assumption about what the adversary would do. And here is now the key point. The key point is that Alice and Bob can themselves enforce the permutation invariant. Because in the protocol, what they could do at the very end is just to say, let's change at random the indices. So what we treated as the first system is now the system pi1, and for some random pi. So essentially, the idea is that if you have even classically, if you have a probability distribution over n different objects, and if you permute them at random, then the new distribution after a random permutation is permutation invariant because you already averaged over all permutations. So the idea is that Alice and Bob just randomly choose the index. And this can be easily done. Alice generates a random table and says, okay, I exchange 1 with 7 and so on, and Bob does the same thing. And this can even be known to the adversary. That doesn't matter, because here we are only talking about the state of Alice and Bob, not of Eve. That comes in the last page. So they can just randomly permute things, and then they are back in the nice situation where this theorem applies, and where we can, at the end, say we have now these product states. So then we are done, essentially, with the proof. So maybe I just repeat briefly how the idea is. So the idea, if you now start from the most general thing, is that a priori we know nothing. The state that Alice and Bob have after the distribution could be arbitrarily corrupted. But now they can just say, let's randomly change the order of these pairs. So maybe they, for example, exchange these two. I mean, both have to do the same, but they can do that at random. Now, if you look at the new state that is generated by randomly reordering them, it's a state that satisfies this permutation invariance condition. And therefore, according to the Definetti theorem, if you now ignore a few subsystems, we are back in this intermediate situation. If you have now this intermediate situation, Alice and Bob can apply state tomography to find out what is the state sigma. And if this state sigma turns out to be the Bell state, the state 0, 0 plus 1, 1, then they are happy and know we can now use all the remaining states which were not used for the test to actually generate a secret key by just measuring it. So the protocol in this sense is quite simple. They just distribute entangled states, then randomly permute them, and then check whether they really have the correct Bell state on a few random samples. And if this test is successful, they just measure all the remaining states and get a key out. Now, I should say that what I describe now sounds experimentally very hard, because you would need to keep everything and permute things and so on. I will now not go into that, but I can just tell you that it's very easy to argue that you don't need to do that coherently. So you can just measure the things immediately once they arrive, and then permute the measurement outcomes accordingly before you further process them. So this is not a technical difficulty to do these permutations. And in most cases, you actually don't need to do them for some other reasons, which I will now not go into. But this is maybe now, let's say, the basic structure of modern security proofs. They usually do these things. So they first make this reduction to the intermediate case, and then they do that. Now, what is usually more difficult than what I presented here is that, of course, in practice, even if there is no adversary, these states will not be Bell states, because there is noise in the communication line and so on. And before I said, okay, let's assume there is no noise, but in reality we have noise. So if there is noise in the communication line, then we have to be a bit more careful about what to do. And we cannot just say it's now, so the lemma that I gave you at the very beginning doesn't apply, because it's just not the Bell state. It's something with noise. But there is still something which we can do, which is quite easy and somehow generalizes the lemma. And this is now, for those maybe interesting who have seen at least a bit of quantum information, but maybe for the others it's still interesting to see how these things work. So the question is, if this sigma AB is now not a Bell state, but something which is sufficiently correlated, maybe sufficiently close to a Bell state, can we still get some secrecy out? So, and you can also see what I'm now presenting as a proof of the lemma that I mentioned before. So what's the idea here? Let's suppose that, for those who have seen quantum information, they have probably seen a quantity which is called the conditional entropy, which is defined as this. It's just the von Neumann entropy, which is sometimes called S, but let me here also call it H, of the joint state of AB minus H of rho B. And so by H of some rho, I mean, as I said, the von Neumann entropy, which is defined as this thing here. rho, maybe I write it here, like that, rho log rho. So that's the definition of the conditional entropy. If you insert into this definition the Bell state, then something interesting happens. The Bell state is a pure state. So the joint state rho AB has rank 1, and for rank 1 states, the entropy is 0. So this term will be 0. The marginal state of a Bell state is just with probability 1/2 a 0 and with probability 1/2 a 1. So it is a maximally mixed state on 1 qubit. So this term is 1. So for a Bell state, you have 0 minus 1. So the conditional entropy is negative. It's -1. And that's just something to remember, to keep in mind. So this can be negative, and for a Bell state, it's -1. Now, on the other hand, if to express that something is unknown to an adversary, we can also use entropy. Yes?
What's the Bell?
Okay, sorry, I said Bell state. What I meant is this state that we had before. So I said I have this 1 over square root of 2 of 0, 0 plus 1, 1. And this I call a Bell state. Yes, sorry for using this slow, or yes, quantum information slang to talk about Bell states. But so one other thing one should know is that what does it mean quantitatively if the adversary knows nothing about the key? It actually means that, so secrecy means that the entropy that we have about, so SA is now again a key. So let's say this is a key bit. Let's suppose we have just 1 bit of a key. And we take the conditional entropy conditioned on the adversary. Secrecy means that this is almost 1. Because 1, I mean, if it's exactly equal to 1, it means that we have a perfectly uniform key bit, which is completely uncorrelated to what the adversary has. That's the perfect situation. So what we want to show is that at the end, the key bit is essentially 1. Okay, now the question is, how can we somehow say something about this quantity? What do we need to talk about this quantity? Now, the first thing that one may realize is that if you do this SA is essentially generated as a measurement from a qubit, as I told you. So it's actually essentially equivalent to say that if I measure the qubit that Alice has, which I called A, and I look at E, so the initial qubit is also unknown to Eve. So this just means Eve is not correlated to the qubit that Alice measures. So this is what we want to show. So that's what secrecy means. Now I'm telling you how we can show that in the case where it's not necessarily a Bell state. And this is a very elegant proof, which is only 1 line essentially, but it shows you how powerful information theoretic techniques are in some way. So let's just calculate this quantity. So what happens if we calculate this quantity? A given E. And now I will use certain things which those who haven't heard quantum information haven't seen a proof of, but I will just mention them, and of course to prove them would be a separate issue. But they are very intuitive things. So, by the way, maybe if I talk about these things, what I'm assuming is always that there is a state underlying which describes what Alice has, what Bob has, and what Eve has. And it's actually convenient to purify this state. So what does it mean to purify this state? I can always consider an additional system, which I call R, such that the state is pure. This is something you can easily verify. Whatever density operator you have, you can always add a quantum system of a sufficiently large size, and then define a state such that if you ignore this R, if you trace over R, you get the original state you're interested in. But if you include the R, it's a pure state. This is something you can always do. And let's, for the moment, assume that. Now, the first property I'm using here is what people call strong subadditivity or data processing, which means that if the interpretation of this quantity is how uncertain is E about A. Now, if I learn, the intuition is that my uncertainty, if I forget something, cannot decrease. So if I forget something, obviously I'm more uncertain about things. And conversely, my uncertainty, if I learn something, cannot increase. If you tell me something, I'm less uncertain. And this is what formally is called strong subadditivity or data processing, and just means that if I add here something, whatever I add here, the entropy, the uncertainty, cannot increase. So we have this inequality. And now comes the most important step in some way. I can now say that this is minus h of A given B. So I will explain this step, but I should say that this is really, in some way, again, the remarkable step, because here we are talking something that involves the system we have not under our control. It's a system of the adversary. Whereas this here is something we have under complete control. This is just Alice and Bob, and they can control their systems. So somehow we can relate the entropy of something we don't know to the entropy of something we know. So why is this step true? Actually, this step is very easy to see. You just insert the definition. So what was the definition? By definition, this was just rho AER minus h of rho ER. And now there is, if the total state is pure, so I said we assume that this is pure, then if you use the Schmidt decomposition of quantum states, you can always see that if I just look at the complementary systems, so here instead of looking at AER, I look at the system B, then it has the same spectrum and therefore the same entropy. So this thing is equal to h of rho B, and this thing is equal to h of rho AB. And now I again use the definition, and you can easily see that it corresponds to this thing. So this is really, again, this is really remarkable because now we have something we have under control. And now this is just something we can directly measure. So now I don't actually need to really proceed, because now we can say Alice and Bob, they can find out as much as they like about the state sigma AB. That's what I said before. They can do tests or tomography. So once they know the state sigma AB, they can, of course, calculate this quantity. And that's why I said before, so this quantity here, if we evaluate it for a Bell state, for the state I wrote, I again erased it, but now you probably know what is a Bell state. If I evaluate it for a Bell state, this quantity is -1. So this means that this expression here is +1, which tells me that I have exactly achieved my goal here. I have now full entropy. But this is now a quantitative version. So if this is not really a Bell state, but let's say almost a Bell state, it has some noise in it, then this is, of course, still close to -1. Maybe it's now -0.9. But then I know still that this entropy is now 0.9. So it's not perfectly secret, but it's still secret. And there are methods to, if I have some secrecy, I can amplify it. This is called privacy amplification. I will now not talk about that, but just that you know, it's not a problem if this is not 1. I just need this to be sufficiently large, and then we can do some techniques to actually get perfectly secure bits out. But the important thing you should see is that this lemma that I mentioned before, which assumes we have a perfect Bell state or a perfectly pure state, can be turned into, very simply, into a quantitative version, which tells you that if you have some state which is sufficiently entangled, so in this case it's a Bell state with, where this is -1, then we can conclude that the system A is completely uncorrelated to E. And this is again this magic step that enables cryptography. So this is really the thing you couldn't do classically again. So it's this equality that distinguishes quantum information from classical information. You can say something about E without having access to it. Okay, so that now concludes, let's say, the part where I talked about what we know. Now I can maybe use 10 minutes to talk to you about what we don't know, which is some way more interesting because it's, I think, more interesting to do research rather than just hearing what people already know. And maybe this now again goes back to a very, in quantum cryptography, a very influential person from Russia again, there's a guy whose name is Vadim Makarov, and he is, I would say, the most famous quantum hacker. So what he does, he breaks the cryptographic systems for which I have proven that they are secure. Which doesn't mean that he's still a friend, but okay. He really breaks these systems. So how can he break them? Because I would still claim that my security proofs are working. So the point is that he breaks the system at the place where he violates an assumption that I'm making in the security proofs. And it's an assumption that everyone makes in the security proof, but obviously it's a bad assumption because he can actually break it. So what's going on? So what he's doing is the following. So if I have a cryptographic protocol, as we said before, we think of somehow abstractly as a theorist, I think of a device. And as I told you before, the way I think of this device is maybe Alice generates, so this is now Alice's device. It generates some entangled qubit and sends this qubit to Bob. And okay, maybe there's some Eve here in the middle that messes it up. And then Bob measures here. So Bob does a measurement of, so the qubit, the photon arrives, he measures it and gets the key SB out. And also Alice measures that qubit. So she measures this. Now what I assumed implicitly in everything I said is that this measurement that Alice carries out, which is, I said before, this is a measurement in the basis 0, 1. And Bob also measures in the basis 0, 1. But how can I be sure in reality that the measurement is really a measurement in this basis? Of course, I could ask the experimentalist who, this is now everything happening in the lab. Let's say this is Bob's lab. And of course, Bob will use some detector. For example, these qubits are usually photons. And in order to measure in this basis, so one possibility is that you have, for example, a 0 encoded into the vertical basis and the 1 into the horizontal basis. Or you could even say that 0 means there is no photon and 1 means that there is a photon. At the end, you use some detector to measure that. And the detector is, of course, completely in the hands of Bob. This is not in the hands of the adversary. That's what we assume. But I'm assuming that this detector that Bob is using is working correctly. Now what Vadim Makarov does is he shines in some bright laser pulse into this device, which disturbs the way this detector works. So the detector no longer measures in the right basis. It's just disturbed by some, for example, strong laser field. So he has even certain attacks where he actually destroys the detector by the thing in a way which doesn't destroy it so that it's no longer usable, but which changes its efficiency to detect photons. So the detector will now operate in a completely different, with different parameters than what I use in the proofs. Of course, if I do the security proofs, I assume I know what this detector does. So he just so essentially what he does, he changes the behavior of the detector by shining in some light, which is maybe on a completely different frequency, so it would be hard to detect here. And the same he can, in principle, of course, do here. So at the end, the assumption that is violated is that Bob measures in these spaces, which really seemed to be a very harmless assumption because that's what we always say. We say, now go and measure this thing. And you could now say, okay, then the experimentalist should just be more careful and really make sure they are measuring these spaces. Now it turns out that this is not possible. It's not possible to have any realistic device which really measures in these spaces under all conditions that the adversary could generate. The adversary can always, you cannot prevent the adversary from sending a strong laser signal into your optical fiber. Of course, you may detect it, but he could use different frequencies and so on. So at the end, you cannot prevent that in practice at all. So that's a fundamental problem. It's not something you can solve by being a more clever experimentalist. In addition, even if he doesn't do that, just by thermal fluctuations and noise and stuff, this detector will maybe not do what it's supposed to do. There are so many environmental conditions that can change it, humidity and so on. So now the question for the theorist is, can we still prove security without assuming that the detector does what it's supposed to do? And this seems to be almost impossible, because if I'm not making any assumptions about what Alice and Bob are doing, then it seems that I'm not able to prove security. However, and this is now mainly the merit of, actually, maybe I should also write the name of Arthur Eckert, who is, as I said at the beginning, one of the co-inventors of quantum cryptography. He realized that actually it's really not necessary to assume anything about these detectors if we are more careful in our analysis. And what he realized is the following, that let's suppose that we don't, this is really just a black box. So we don't know what's inside. Of course, the experimentalist created it and knows what's inside, but I'm now doing the analysis, and I don't want to make any assumptions about what the experimentalist did. That's now I'm really safe in some way. I'm not putting in any assumptions. But now, of course, in reality, what's going on is that still the experimentalist tries to generate Bell states and measure them in a certain basis. Now, I come back to the reason why they are called Bell states. So they are called Bell states because they're used for Bell tests. I don't know whether you're familiar with Bell tests, but Bell tests are a way to check correlations between two systems which you cannot regenerate classically. So essentially, the idea is something like, I could use this box and say, measure in one of two different bases. And let me now just change this into an A and this into a B. And just think of the following scenario. I give you a box. It gives you a choice of how you want to measure. And the choice is just one bit. So there's a bit you can choose. And then something is happening in the box, and what you get out is again a bit of information. And Bob can do the same thing. He can choose something, let's call it Y. It's again a bit. And he gets out of the box something which I call B, which is again a bit. Now, you only see that. Let's suppose you know nothing else. Now there is what Bell essentially realized is that just by looking at the correlations between A and B, we can be certain that they were not generated with a classical non-quantum device. And even more, we know today that by just looking at the correlations between A and B, we can actually infer that the state that was inside the devices, which must have existed to generate the correlations, was actually a Bell state. So in some way, what we can do today is just by checking the correlations between the inputs and outputs, derive rigorously that in these boxes, at some point there was a Bell state that was measured, which is exactly the goal we want to achieve. But maybe to give you, okay, these were now just words, to give you just an impression of how this could work, let me make some small table. So this is just maybe a way to see the Bell test experiment. So an extreme form of the Bell test, which is actually not even achievable with quantum mechanics, but in a noisy way it is the following. Let's suppose that you do this, you have these boxes, and you now do statistical tests. And let's say you make a table, and on this table you have the different inputs. So on X you can input 0 or 1, and on Y you can also input 0 or 1. Now, let's suppose that what you find out is that there's always some random bit coming out. Maybe you don't know whether it's random, but you realize that whenever X and Alice and Bob input the 1, then the outcomes that Alice and Bob get are identical. And also, if they input, if Alice inputs a 1 and Bob a 0, they also get identical outputs, and here as well. It's kind of boring, they always get the same, but except here, if both of them input the 1, then the outcomes are different. Now, what you should now realize, so this is, let's suppose you have a box which does that. Actually, it turns out that with quantum mechanics, you can realize something which does that with high probability. Not always, but with a probability that is pretty large, close to 1. Now, actually, if you think about it, what did I mean when I say this couldn't be a classical box? What it means is that there is no way you can actually assign values to A and B. So let's suppose you would now be asked to program such a box with a classical computer, which regenerates this behavior. Then you would necessarily fail. Because what you can do is, of course, the A value can only depend on x, because it only, in this box you only get the x as an input, and the b value can only depend on y. So now you find no way of letting a depend only on x and b depend only on y in such a way that you can fulfill these constraints. This is just impossible, and it's very easy to verify that it's impossible. Actually, you can even say something stronger, and this is where it goes to cryptography. Let's suppose you want to know what is the probability of, let's say, that a has a certain value. Let's say you want to know what is the probability that a is 0 if x is 0. And let's say you know anything else. Now introduce again if. Let's suppose we have some if e. Now I can do something which is maybe, again, a bit surprising. Let me not always write the e, but let me just say, of course, this probability distribution. So what is the probability of a equals 0 and x equals 0 should not depend on what is y, because that's completely a behavior of the box on the left-hand side. So whatever I do on the right is not possible. This is, by the way, the so-called non-signaling assumption, which still enters. So I'm assuming that whatever I do on this box, as long as I'm not communicating between them, so I distribute the entanglement, but then I close them and don't communicate, then the behavior of this box cannot depend on what I'm doing, what I'm inputting on the other box. So I can put here a 0, if you like. And then I can now say, in this case, the table here tells me that a is equal to b. So I also know that b is equal to 0, conditioned on x equals 0 and y equal to 0. But now I can actually change the value of x, because, of course, the behavior of the b box doesn't depend on x. So I can write here x equal 1, and here keep the y equal 0. But now I can again look at the table and say, if x is 1 and y is 0, then a and b are the same. So I can again write here a equals 0. Okay, now it looks as I'm turning in circles, but actually I'm not. So now I write here x equal 1. But now I can again change the y value. So I can, now I'm talking about a. Now I can say, let's look at y equal 1. But now if I look at the table, it tells me that if x is 1 and y is 1, b is not equal to a. So this must be equal to the probability that b is equal to 1. So the probability that a is 0 is equal to the probability that b is 1 in the case where x is 1 and y is 1, because a and b are always just the opposite values. And now I can again go back and turn around and say, okay, now I go back to it. Okay, I can repeat these steps, and at the end I have again here x equals 0, and here a equal 1. So this is just by, again, doing another step of the same kind. I mean, you see the principle. But what I have now shown, I've now shown that this probability is equal to that probability. And I didn't write the e always. So there was always also given e. But what does this tell me? If the probability that a is 0 is equal to the probability that a is equal to 1, then this means that the probability of a equals 0 must be 1/2. So what I've proved here is that conditioned on the adversary's knowledge, a is just completely random. So in some way, this is remarkable. By just knowing that the output statistics of a and b satisfies these constraints, I can prove that no one, so if is someone, no one can actually know the value of a. It's just uniformly distributed. So, and this is what Bell somehow tells us. So Bell's inequality tells us that we have certain constraints which we can see experimentally, and knowing these constraints, we can know we have perfect randomness. Now, what is the challenge here? The challenge is that this is a nice principle which works in the perfect case, but we don't know, and we already have security proofs for this in practice, like almost practical schemes, but we have no working thing like that. So I told you before that quantum cryptography is something you can buy. But you can buy a scheme which proves security, assuming that the measurement device works according to the specifications. And as I said, this is in practice actually not the case, which means that if you now buy a crypto system in practice, it will probably be insecure if I can call Makarov and he will hack it. So we want really to have security without this assumption. But here, the proofs are more the quantitative proofs. This is now just a kind of qualitative argument. But the quantitative proof of this type here are still not good enough to reach the regime where we can actually implement them. And this is now
Even with entanglement, you are still not sure that Makarov effectively can break it.
sorry?
Even with the illusion of entanglement, even with using this accurate idea,
Yes.
you are still not sure that Makarov.
Yes, that's a good point. So he may find another assumption which we are making, and actually there are still assumptions we are making. For example, one assumption we are making is that we can still freely choose what to input here. If Makarov can change my mind and make sure I always input the same thing, then he can still break it. But it's pretty safe. So
The intuitive feeling is still, even if you work with the entanglement state,
yes,
something in your entanglement is again.
yes, yes. So this is a good point. So actually, the reason why it's so hard is maybe people here have noticed that 2 or 3 years ago, 2.5 years, there was the so-called first loophole-free Bell test. This is a Bell test where you really make no assumptions and somehow verify that you have such correlations. But now, no assumptions is a too strong word. So they still assumed they could freely do the experiment, freely choose the measurement basis. So there are some assumptions, but they're pretty weak. So I would say that if we have that type of security that I want, only based on this, then we have a very high level of security which is based on very clean assumptions. Whether the assumptions are satisfied is still a question, because as I said, the assumption is still that we can freely choose this input. This input here is random. So how do we make sure it's really random? But at least we know under this assumption it's secure. So let me just therefore conclude by saying that proving security under these weaker assumptions where we don't make an assumption about how the measurement looks like is still an ongoing process. And there has been a lot of progress, but we are not as far as having an actual implementation and a corresponding security proof. And this is a challenge both for experimentalists to actually do better experiments with entanglement, to get better statistics, but also for theorists to actually compute how does the noise, in practice we'll have noise in this table, how does the noise influence this quantity? So somehow what we need to do technically on the theory side is to have a lower bound on this quantity, like here, which depends on how well these correlations are satisfied. That's what one has to do. That's really the task. Now there's another thing which I also actually initially thought I will talk about, which is a technique which replaces the Definetti theorem, which you need here, because the Definetti theorem doesn't apply here, which is called entropy accumulation. But now I'm sorry I couldn't talk about that. But let me say that this is now the big challenge in quantum cryptography. And there are many people working on that. And if you look for a keyword, this is called device-independent cryptography. So that's essentially, let's say, the summary of the challenge. We want to have a device-independent quantum cryptography scheme. So that's what I have to say. Thanks a lot for your attention. Okay.
So please question. We have still some time, but
Yes.
a little bit late.
Can you tell us anything about the latest achievements connected with quantum cryptography at your university?
Mm-hmm.
And the second, is there a research connected with post-quantum cryptography?
Mm-hmm. Okay.
At your university?
Yes. Okay. So at my university at ETH Zurich, we are, of course, working on a lot on quantum cryptography on the theory side. And what we are recently were working on is exactly what I now didn't talk about in some way. So I talked about everything else except what we are actually now doing, which is, I told you before that in order to get to a provable thing, we need to go from this messy situation. I just draw the sketch. So we had this messy entanglement stuff. We wanted to go to a clean situation like this. And I said we are doing that using the Definetti theorem. Now, the problem is if you go to the device-independent scenario, the Definetti theorem doesn't apply because not only the state could be now messed up between the instance, but also the measurement itself. You could think of like the device doesn't measure the individual photons, but it just maybe correlates them. That could happen. And now it's not only the quantum state that is messed up, but also the measurement operator. And this cannot be captured by the Definetti theorem, which is a theorem about the state and not about measurements. So what we are doing is to say that still we can go from here to here, and there is a technique which we call entropy accumulation. And what this actually says, very roughly speaking, is almost the same, is as before, but not on the level of the states. It's telling you that if you want to know, so at the end, as I mentioned before, we want to know what is the entropy somehow of whatever Alice has, now for all n things, based on what Eve has. And this is usually very hard to evaluate because this is a huge system and it could be a big mess. So, however, if we could decompose it, it would be much easier. And entropy accumulation tells you that entropy accumulates in the following sense, namely that h of A1 until Hn given E can essentially be written as, or bounded, you need a lower bound, by looking at the entropy of the individual A's. So this is just what you have in one round, conditioned on somehow on the E. But here I have to put some infimum over the E, so you always assume that Eve does the best thing for the individual round. So essentially, this theorem tells you that this huge object, which would be a high-dimensional Hilbert space, which is very messy, can be analyzed by just looking at one such thing and analyzing that in detail. So there's a theorem. That's now a very informal version of the theorem. But essentially, the theorem tells you that, and that allows you to go again from the messy situation to that one. This theorem, by the way, this is really very current research. This will, in January, there will be a paper appearing in Nature Communications where this is in and where we give plots, which then hopefully would bring experiments closer to the realization. So that's what we do. We do these type of things. Now, the other question, whether we do post-quantum cryptography, then I would have to ask back what you mean, because there are two, the word is used for two different things. One is to make classical cryptography secure against quantum computers. That's what you meant, because some people also used it actually for these type of things. Okay, so this is research which is at least in the groups I'm familiar with, and I have close connections to, for example, the group of Ueli Maurer, who is a well-known classical cryptographer, is not at this point done. And on the other hand, there's a huge community now being interested in that. My personal opinion is that this is extremely important to be done now, because we need so even if a quantum computer will only be realized in, let's say, 30 years, we need at least 10 to 20 years to set up the infrastructure for a new crypto system. So we would already be too late if we had a new one today. Because if I encrypt the message now, today, of course I want it not only to be secure now, today, but maybe for the next 10 or 15 years. So if let's say in 15 years, so let's say we would now change the infrastructure, and it would take us 15 years to change it. And then in 15 years, I still, just before the change, want to use current cryptography and encrypt something, and want this still to be secure for another 15 years, then I'm already with 30 years. So if in 30 years there's a quantum computer, we need to change the infrastructure now or start changing it. And so that's why I think this is very important research, which is, however, not really something you do in quantum. So this has not much to do with quantum. Of course, the motivation is quantum, but at the end, it's really about finding new alternative classical cryptographic schemes. And of course, quantum cryptography is an alternative, but it's a very expensive alternative because you would need a completely new infrastructure with optical fibers, and you would also need quantum repeaters to go to long distances. Currently, we can only do it over a few 100 kilometers. So at the moment, this is not a workable alternative, but it would be one if it was cheaper. But I think at the moment, we need to explore other alternatives as well. But this is not done at ETH as far as I know.
Is related to this Makarov hacking.
Mm-hmm.
And as far as I remember, you have said that Makarov sends the lasing pulse at a different wavelengths. So is it possible to naively make the line secure by adding some bandpass filters or something?
Yes.
Like that?
So this is actually, let me give a more general answer to your question. So the short answer is yes, you can prevent that, but the problem is then you are in this typical, I call it vicious cycle between attacks and countermeasures. So the problem is whenever you do something, and this was done, he finds a new way to attack it. So what we want is really to have something where we can prove that whatever he does, we cannot do anything. So that's the whole point of quantum cryptography. Of course, even in classical cryptography, whenever it was broken, this is the whole history of cryptography. Whenever something was broken, people came up with a new scheme. There were more clever attackers, and then it was again corrected. So quantum cryptography has the aim of escaping this cycle. So we would not be happy with such a solution. But it has been done. So for example, ID Quantic, the company, does some measures which prevent his first attacks, which are kind of trivial attacks. But of course, he's very clever, so he can always do other stuff. And he has shown that there are many other things you can do. So for example, there are time delay attacks where you just use the fact that the detectors have different efficiency depending on the time, because they have time windows. So you just cleverly delays the pulses a bit by an appropriate time, and then he can again influence the detection efficiency. You see, this has nothing to do with the frequency, but if you have a frequency filter, it just moves to another thing. So this is not a good solution. And that's why we are so interested in device-independent cryptography, because there are still assumptions, but they're very clean. It's not just, we have prevented a set of attacks. We have very clean assumptions which we can reason about whether they are actually sensible or not. And if they are not, we can still try to strengthen or weaken them in the sense that we have stronger security.
Okay, that is very good news, because that is what it can have job for years.
No, the goal is exactly to escape that. So I destroy the job of these guys. Thank you again for the invitation.